Hello, everyone. Welcome to another episode of Serverless Sorcery, where serverless meets generative AI. Today, we have an exciting talk about WebAssembly within the serverless and generative AI space, and we're joined by Matt Butcher. Matt Butcher is co-founder and CEO of Fermion, the serverless WebAssembly in the cloud company. He is one of the original creators of Helm, Brigade, CNAB, COAM, Glide, and Crustlet. He has written and co-written many books, including Learning Helm and Go in Practice. He is a co-creator of the Illustrated Children's Guide to Kubernetes series. These days, he works mostly on WebAssembly projects such as Spin, Fermion Cloud, and Bartholomew. He holds a PhD in philosophy. He lives in Colorado, where he drinks lots of coffee. So, Matt, welcome to the show.
Thanks. I'm super excited to be here.
Great. And we're really excited to have you too. So, Matt, do you want to tell us a bit about what we're going to be talking about today?
Yeah, I mean, this is a serverless podcast, and LLMs and AI are another passion of ours. So I'm really excited because we Fermion started a couple of years ago, and our kind of core intuition was that serverless had a ton of potential. And a lot of it had been realized, right? We developed the right coding patterns, but we hadn't quite found the right compute platform to sit underneath this new coding pattern. So, I think we'll start there. We'll probably work our way into some of the interesting stuff we've done with AI and LLMs more recently, and talk about sort of why we think that WebAssembly really is sort of the future foundational technology for this next wave of serverless and AI inference.
Definitely. Thanks, Matt. And I think a lot of our listeners will find this very useful as well, especially because we haven't really talked that much about WebAssembly in the generative AI and the serverless space as well. So I do feel that there's a lot of potential that can be brought from this. So getting us started out for a bit, can you talk a bit more about what got you on this journey to being able to utilize WebAssembly within the serverless space, lead to the creation of your project Spin and SpinKube as well?
Yeah. So my team, the first 10 people from that started Fermion, we all came out of Microsoft. And actually a bunch of us went even farther back. And we were at a startup called Deus that was a very early Kubernetes company. And at some point, Microsoft was trying to build a great Kubernetes team. And they looked at our little Boulder startup and said, we'd like you to be part of the Microsoft team. So they acquired us in, I don't know, must have been about 2015, 2014, 15, 16, somewhere in there. And this team became part of what is now the AKS team at the Azure Kubernetes service. And we were kind of split in two. Half went and built services. That was not the team I was on. My team was like the open source upstream team. We did a lot of R&D work. We went to a lot of conferences. It was really cool. We kind of got to go visit a lot of Microsoft customers. And as you know, like Microsoft works with tiny startups and Microsoft works with the biggest companies in the world. And it's like when you can just go visit them and walk in the door and be like, so what are your problems? What problems are top of mind for you? What kinds of things are you trying to figure out how to solve? And then just listen to companies large and small sort of just dump these are all the things that are frustrating to us. We wish we could do this. We wish we could do that. And so our job at Microsoft, my team's job at Microsoft really became going to conferences, going to customers, visiting internal Azure teams, and finding out sort of what were the hard problems for them. And then seeing how we could solve those with cloud technologies like virtual machines and containers and Kubernetes. And I really think, and really genuinely think, this was absolutely the best job anybody could have at Microsoft. It was just very invigorating. We got to try lots of things. Honestly, we failed quite frequently to figure out how to solve particular problems, but learned things and then turned those around. I think in the end, we contributed something like 9 to 12 projects to Cloud Native Computing Foundation and Linux Foundation, which are big, open source foundations. It was just an awesome job. But anytime you're asking a lot of open-ended questions like that, you're going to start to collect some problems that seem intractable, right? That seem impossible to solve given the technologies we had. And this is sort of what initially got us turned on to WebAssembly. So we were serverless, of course, was really kind of has been taking off. I mean, for 10 years, we've watched it get more and more popular each and every year until I think it was a couple of years ago, Amazon said they execute something like 10 trillion Lambda functions a month. I mean, that is a truly staggering number. And inside of Microsoft, we were looking at the same thing. They've got Azure functions. We were seeing lots of frameworks developed around serverless. But as we got to talking to people who were responsible for building the serverless infrastructure, we started hearing the same story over and over again, which was, yeah, it's a cool technology. Developers absolutely love the developer paradigm, the pattern, but the compute layer is really clunky. And we discovered at one point that, and I found out recently, this is also true of the way that AWS Lambda works as well, that in order to serve things out quickly enough, they cannot afford to cold start a virtual machine fast enough to load the Lambda function. So they have a giant queue of virtual machines that are sort of vanilla virtual machines that they spin up and they leave in this queue. And as a request comes in, a virtual machine gets popped off the queue, the workload, the serverless function gets dumped onto this virtual machine, executed, returned, and then in the case of Azure functions, it destroys the virtual machine and creates a new one and pushes it on the end of the queue. So essentially, you've got this huge queue of servers that are just virtual machines that are just sitting there doing nothing while they're waiting for requests. And you have to keep that queue full because they have to be ready to go right away. Otherwise, you're talking about a fairly major performance penalty if someone were to make a request. And so we're listening to this architecture and going, this is not the level of efficiency that we should aspire to, right? What if there's some runtime out there more efficient than virtual machines, which take several seconds up to minutes to start, or containers, which tend to take around a dozen seconds to start? What if there's some kind of runtime out there that would be faster, but still have the same super strong security profile, still be able to support a wide variety of languages and system architectures and operating systems? And this led us and this is while we were still at Microsoft, this led us on a quest to try and find what this third kind of cloud computing layer would be. And we looked at a bunch of things. We actually talked about inventing our own thing. But ultimately, one of the engineers on the team is like, hear me out. There's this technology called WebAssembly. And we're all like, the browser thing? And he's like, yeah. The security model's great. The cold start time is amazing. The language support is really good. It can run on any operating system and any architecture out there. We could just pull it out of the web browser and plug it in on the server side and build a serverless platform out of it. So, we started looking into this, and it turns out that even in our very early days, the cold start time we could get off this platform was about 100 milliseconds. Now, your typical Lambda function is 200 to 500 milliseconds for a cold start. Azure function is a little bit higher than that. Some of the OpenWhisk and other open source variants way higher than that. And so we were looking at this going, well, already we're faster than the current market leader. And we started playing around with this and optimizing it and experimenting. And at this point now, and granted it's 3 years later, we're down to about a half a millisecond for a cold start on these things. And this is just because WebAssembly, the technology, was built to start really fast, whereas virtual machines were built to run an entire operating system from, kernel to application and everything in between. So they're built like a battleship. These things were built like speedboats. They're designed to be very, very fast. WebAssembly's runtime is designed to start fast, to keep things in memory for the minimal amount of time necessary. And so we looked at this and went, oh, this just seems like the right technology. We pitched it internally at Microsoft. Microsoft wasn't terribly interested at that time. Since then, they've changed their minds. But at that time, I think we were just too early to really pique their interest. And so 10 of us left Microsoft on the same day and went and started Fermyon. And the idea was, can we build a company around the idea that we've got an open source platform to run serverless functions that are faster and more flexible than what anybody else has achieved to date? And if we can do it, then what kinds of new things can we explore in the serverless world?
Definitely. It's certainly a really great thing that you explored that processing power that was able to be achieved from the cold start, because I do feel that with the workloads that we have today, it's becoming more and more of a big concern being able to achieve that at scale, especially with a lot of serverless workloads now being discussed going into the Gen AI space, it's
Yeah.
becoming more and more of a very important thing because, well, a lot of people are still trying to figure out like what workloads should I use? Can Lambdas work with my starting times? Like,
Yeah.
how can I get the outputs from Gen AI quickly when it comes to trying to serve our customers? So I think it's a very great point that you brought this up.
And I think that, yeah, I think it's important to recognize what's happening, right? In that, again, the paradigm, right? The serverless, let's call it a design pattern, right? The application pattern that a developer uses to write it is simply like, instead of having to write a long running process that's going to spin up and handle tens of thousands or hundreds of thousands of requests, I just write a function. And the function takes a request and it does its processing and it returns a response, right? And that part people know and love, right? And rightfully so. It's so easy to do, right? Like all the boilerplate code that, process management and socket management and all that is just gone. But then the underlying piece is the compute layer, right? And so when we were talking about a compute layer, what are we actually talking about at a technical level, right? Well, we're talking about an environment where untrusted code can be supplied by anybody, right? And we can execute it in a way where, well, let's say it this way. I can execute my code and your code on somebody else's machine, and you can be confident that I can't do anything dastardly to your application. I can be confident that you're not going to do anything dastardly to my application. And the person who's running the hardware that we're both running on knows that neither of us can attack their platform, right? So you got this security layer. And that's kind of piece one of what you need as a serverless compute platform. And then piece two is sort of like you need a computing environment that effectively manages memory, CPU, and other system resources. And when we started Fermyon, we were really thinking about other system resources being like network and volume management and stuff like that. And we were thinking of CPU as being sort of the core kind of compute. The cool thing is that kind of light bulb moment when you go, wait a minute. AI is just another form of serverless compute. It's just another form of compute, right? You're using a different kind, often using a different kind of processor than a CPU. You might be using a GPU or something else, right? Well, you might be using a CPU for it, but in effect, the kind of management you're doing with GPU resources is not at a compute layer fundamentally different than what you're doing with a CPU. You want to be able to have multiple tenants using the same processing resource, but in a way that protects them from each other and protects the host from the things running in that environment. So, as we got into WebAssembly initially, we were thinking primarily in terms of traditional compute workloads, right? REST servers and, content management systems and, event processors and stuff like that. But as LLMs began to get traction, as other forms of AI, generative AI started to get traction, we realized that actually the WebAssembly is a really good fit for those style of workloads as well. Because again, fundamentally, it's the same kind of thing. And so to us, the big advantage and that kind of aha moment was realizing, oh, people like serverless as a design pattern because it's fairly easy to do. We can abstract away a lot of the pain on the hardware layer and make it so that they can ideally write a piece of code that runs without even knowing necessarily what the underlying GPU architecture is, whether it's, CUDA and an NVIDIA CPU or a Mac Metal GPU or kind of whatever, right? I keep saying GPU and CPU so fast that I'm starting to get confused about, but again, well, and CPU inferencing is another good example. You shouldn't even have to know whether you're inferencing on a GPU or a CPU if you've built the right abstraction layer, right? And that's where I think WebAssembly is very exciting because it can take these kind of serverless workloads and be able to provide the right abstraction layer between the hardware and the virtualized guest code. And I, as a developer, never have to know what the underlying architecture is. I just say, I want to run this inference on this particular large language model or whatever, and it delivers it to me. And, somebody in the operations team decides on whether or not I'm getting a super high speed, very fast, expensive, NVIDIA GPU or whether I'm running on, a slower CPU.
Right. I think that's something I really appreciate as well from seeing the security model from WASM, particularly its capability-based security design, being able to have that sandboxing and having by default denied access to resource on the system,
Yeah.
I feel is a very powerful thing, especially in the context of generative AI workloads on serverless, considering that it's becoming more and more of a going concern. It's how we limit access to these models, how we prevent vulnerabilities to these models and in accessing these models on our own systems. So I think it's a very great thing that WASM is able to provide that capability-based design. And I think you really touch on a great point there.
Yeah, and probably it's a good idea to describe capabilities design, because I think there's some older notions about it, and the newer way of doing it is kind of interesting. And it actually goes back to the design of the web browser, right? So the original problem that WebAssembly was intended to solve was to allow people to, take existing code in languages other than JavaScript, compile it to this, platform neutral bytecode format called WebAssembly, and then run it in the browser and be able to use JavaScript to call in and out of it. Now, I actually thought this story was mythical when I was at Microsoft, but since leaving Microsoft, I've been told this is a true story. That in Office, there was, when they were porting Excel over from its original C code base into running it in the browser, there was some particularly gnarly library that was written. The story goes, it was written in the 1980s. And it had been maintained for some period of time, but the original team that had written this library had long since retired, and given Microsoft stock prices, probably own private islands somewhere in the world. And yet this library was pretty fundamental to the way that Excel functioned. So here was something that it was very difficult for new people to pick up, but also, kind of fundamental for running it in the browser. And so they used WebAssembly to compile some 1980s C code into bytecode, WebAssembly bytecode, and then plug it into the browser, and the JavaScript could call in and out of this. Now, the security model here would say that what you don't want is to compile code you don't understand and run it in your browser and have it be able to do, again, dastardly things to the environment around you, right? You wouldn't want this thing to be able to call out to your operating system, load random files. You wouldn't even want it to be able to be used as an attack vector against your JavaScript code, right? So the security sandbox has to be really, really strong. So by default, a WebAssembly binary can do very, very little. It can access very, very little of the world around it. In fact, it can't even get the system time or access environment variables by default. And this is a really good design because, again, you start with the strongest security controls. Then you give it this capabilities model where you can say, I'm going to turn on this particular capability, or I'm going to give it a limited access. I'm going to give it limited access to this particular capability, and then the code can do something more interesting with that kind of thing. So for the simplest example is, I'm going to let it access the clock time so that it can find out what time of day it is and do a calculation based on that. But far more complicated examples would be network access, file system access, GPU access, and that kind of thing. So the original WebAssembly standard has no real notion of how to do this capabilities thing. It's basically, the original standard is it is locked down, and you can import and export a couple of JavaScript function calls, and that's about all you can do. But the WebAssembly system interface, WASI specification, basically said, here's how we overlay a really nice system interface that we can turn capabilities on and off for. The original version was environment variables, clock time, file system access. I'm forgetting one or two, but very, very basic operating system-like things. And so you could suddenly say, all right, this piece of code is allowed to load some environment variables. These are the only environment variables it's allowed to load. So the guest code, the piece that I'm writing, right, to run inside of this environment, just uses its regular getenv, setenv kind of functions that are built into the language. And then the runtime sort of mediates and says, oh, well, you asked to getenv home. Well, I'm allowed to give you this value for the environment variable home. You asked for getenv, password. I'm not allowed to give you anything called that. So I give you back an error message that looks like a file or an operating system error. So essentially, when you're writing the code, it feels like you're writing just regular old code. with regular old APIs. But the WebAssembly sandbox is basically mediating. So when we talk about capabilities-based security, that's what we're talking about, is this ability to let the developer write code the way they always write code, but the sandbox environment to sort of intercept it and say, yes, you're allowed to have that. Yes, you're allowed to have some version of that, but not all of that, or maybe a fake version of that, or no, you're not allowed to have that at all. And that I think that capabilities model is what's proven to make WebAssembly a really good fit for the cloud. And also, more specifically, as we've done at Fermyon, it makes it really nice to be able to say this WebAssembly binary is allowed to use this LLM, but not that LLM, or it's allowed to inference like this.
Right. And I think it's a really great thing that you define capability-based security design, because I feel like it's certainly more so these days of a WASM concept, I would say, compared to a lot. It's present definitely within other systems, but I think it's very a core part of how WASM works, I feel, in terms of security. So I think it's a really great thing that you defined it. Shifting our discussion a bit, talking about your own experimentations with LLMs as well, I was wondering as well, what kinds of LLMs have you experimented with, whether they be out of the box, whether they be open source models, and how have you been going around with using them within WASM?
That is a great question, because we're all kind of struggling with renegotiating what the landscape looks like when we're dealing with language models and not just source code, right? And there are even some good debates over what we mean when we talk about an open source model versus a proprietary model. And that's a question I'm not equipped to answer. But when we got looking at supporting models, I think the first one we started with was Alpaca. And that was the one that Radu's our CTO and the co-founder with me. When Radu first started writing our AI inferencing, Alpaca was the first model that he used for that. But we realized that we weren't entirely sure whether it was open enough to be able to, use it in a hosted environment like Fermyon Cloud. And so what we decided to start with was a model where we were clear from the license when we could run it, where we could run it, and what the limitations of all that were. And Meta had done a really good job with the Llama 2 library of articulating very clearly what the constraints were for running. And so we started with Llama 2 and Code Llama. And largely, if you were to go create an account on Fermyon Cloud today, which is one of the ways you can do AI inferencing in Fermyon, you would find Llama 2 and Code Llama automatically available to you out of the box. You wouldn't have to do anything. And then we made Spin itself more flexible. And I don't even know what all the models are that we currently support, but it's far more flexible than just being able to support 2 models. And ultimately, the new work that we're doing inside of Kubernetes environments would allow you, the Kubernetes administrator, to bring whatever large language models you would want in there. I think that, and then, of course, I should caveat all of that by saying this is when you're talking about bringing your own model, right, and loading it into your system and using your GPUs, or in the case of Fermyon Cloud, using Fermyon Cloud's GPUs. If you just want to do API-based inferencing, you could basically use whatever API-based. So OpenAI, all of those would work just as easily. But that's because you're running the inferencing on somebody else's hardware. But I think it'll be interesting over time to see how this kind of shakes out. Because for us, the most important question has been, how do we deal with the intellectual property rights of these various models? And how do we help users be responsible without forcing users to do something they don't want to do? And in the case of Llama 2, we went, okay, if we're going to host this model on behalf of other people and run it there, then we're going to start with one where it's very clear from the license that we are well within our bounds and that users are well within their bounds to use it. So that was kind of what led us that way, even though, I think there are good arguments to be had that Llama 2 is a good solid model, but maybe not the best model out there or the best general purpose model.
Right. And speaking about the challenges that you mentioned on how you can prevent, for instance, like user small intent and using these models, have you had any particular challenges, you'd say, in these areas, or can you speak a bit more about that as well?
Just in terms of what kinds of models people have wanted to use and how they've wanted to use them, I would say actually that is probably the biggest challenge for anybody doing what we're trying to do, right? And what are we trying to do? Well, we're trying to provide an infrastructure layer for other people to do AI inferencing, and we're trying to do it with good, solid abstraction so that, again, you as the developer don't have to know whether you're running on an H100 GPU or on like an Ampere ARM CPU cluster, right? You shouldn't have to know whether you're running, and you shouldn't have to change your code to run on any of those. That has presented some interesting challenges. One of which is probably the most obvious, but also least obtrusive, is that if you're really into tuning very specifically for your architecture, that's just completely out of bounds, right? It's just not a thing you can do with WebAssembly. Most people, I think, are okay with that, particularly on the inferencing side, where we're all trying to explore the cool class of applications we can build. For most cases, we're not yet at the point where tuning a particular handling of a particular architectural detail is something we care too much about, right? I will get there, and it'll, I think, over time mean that we'll have to figure out increasingly interesting ways to allow people to tune at low levels. But at high levels, that hasn't been a thing that most people seem to care about too much. The other thing that's difficult at this point is that the standards are emerging on how all these models will work, but they're not there yet. And people tend to want to do some fairly intense and interesting things with these models, many of which are outside of the scope of what we thought they were going to want to do. So, for example, some people might not want to pass strings in and get strings out. They might want to pass in structured data and get structured data out. There's no generic interface we've found yet that'll satisfy that particular kind of requirement. And I think the third challenge has been maybe a little bit of a surprise to us, in that the landscape is evolving so quickly that it's very difficult to kind of keep all the different tool chains working well. So we focused on some Python stuff. It was all working for a while, but everything's evolving so quickly that we have to really stay on top of it in order to keep everything functioning at the level that users would expect. And I mean, we're used to moving pretty quickly because our entire industry moves pretty quickly. But right now, I mean, it's an all-out sprint. Everybody's just charging ahead as fast as possible to try and push the limits of the technology, to try and find a niche in the market, to try and improve the model before people get tired of its deficiencies. All these things are just going so fast. And that has been a big challenge to keep up with at the infrastructure level, because what we want to provide is a fairly solid basis, but meanwhile, everybody else is kind of charging ahead at a breakneck pace. And that's a hard balance to find and try and strike. To that end, though, it has helped to limit the number of models in this initial phase and be able to say, we're just working on Llama 2 on Fermyon Cloud, or Llama 2 and CodeLlama. Because then we can say, all right, well, we only have to move at the pace of one LLM, even though at the same time we're trying to support lots of different libraries.
It's certainly been the advent of a lot of companies trying to go into using these foundational models, try to innovate and get ahead of their competitors, I would say. So I think you really touched on the fine point there. And I feel that a lot of the providers of these foundational models are very aware of that as well. And that's why as well, it's, with big events such as like reInvent Now or from AWS or other similar conferences as well from Microsoft too, for instance, the topic has just been about Gen AI all the way. It's been like always just fully Gen AI, and I feel like it's going to continue on being a while, at least for this year as well. So
I agree.
I feel it's certainly an interesting thing, and I do feel that the need to innovate is quite outpacing the steady development cycle. And I mean, another thing you touched on as well for the continuous updates, I feel it's a very good point as well, because I think to the listeners who are tuning in as well, like people who are already worked with different APIs, such as OpenAI's APIs, for instance, for like working with their GPT models, they would also know as well. It's already been shifting so much from when they made their initial release up to now, and I've already lost count of how many times I have to update the API, the code for the API.
Yeah, I know what you mean. Yeah,
yeah, it's crazy. It's like you don't pay attention to it for a while, and suddenly when it comes to the newest version, and now it's like everything's changed again. So I feel it's just a very continuously evolving base that everyone has to keep up with, and I feel
Yeah.
that's one of the biggest challenges in my opinion too.
Yeah, and I don't want to come across as complaining about it, even though I kind of am. And the reason why is because we've seen this happen not just in technology, but in science, throughout history, right? Where you tend to hit stable states and you tend to hit innovation periods, right? And science, I suppose, in many ways, the pace was limited historically. Like if you were to go back and look at even like, when Einsteinian physics began to encroach on Newtonian physics, right? Lots of brilliant people working on this stuff and new innovations happening very, very frequently. But in some ways, the limiting factor at that period of time was that they couldn't transmit information very quickly, right? Their primary ways of transferring information were publishing in paper journals, which have like multi-month cycles, and going to conferences, which have long planning cycles. We've basically eliminated all of those kind of like communications hurdles. And now, we can all collaborate, instantaneously over a video conference and commit our code in GitHub and have it unit tested and shipped out within, in cases, hours, minutes, days, whatever. The turnaround time is no longer limited by communication. And in a way, it's meant that in technology, we've seen things be able to very, very rapidly progress, right? And I think this is one of the bigger technology shifts that we've seen, in the sense that it's unlocking so much potential, and development can happen so fast. And in a way, we still don't exactly even have a good grasp of what all we can accomplish with this technology. That means we're basically moving at the speed that our medium allows us to move at, which is very, very, very fast. And so it's good because we will get farther faster. It's bad because people like me are like, yeah, but I just want something stable that I can use for a couple of months, right? But I would trade off the speed thing, right? I'd gladly take speed over having to deal with a limited system for a longer period of time. It'll be interesting to see how long this kind of swing lasts, right? If you look at the web, I'm old enough that I was in my first programming job was happening right when the web was really taking off. And we were working on static HTML sites and Perl scripts, right? Were the two technologies that I used most frequently. JavaScript was not yet mature enough to be able to do much more than, make a message pop up occasionally or something like that. And then in like a 5 to 10 year window, it just absolutely exploded. And we went from this kind of marshmallows and toothpicks technology where you always felt like you were kind of building a tower that was in danger of tipping over if anybody, sneezed too hard. And then suddenly we were at like enterprise Java beans and J2EE and all these very sophisticated large technologies. And now, the web technology is such a robust area that we don't even think about sort of like the foundational pieces of it anymore. We have, React and frameworks like that for the front end. Java is deeply entrenched at every large organization on the planet. And we've got technologies like Express.js for building rapid websites and stuff like that. It's easy to forget that actually took like 10 plus years to get from zero to there, but also to forget that we iterated hundreds of thousands, probably millions of times, and a variety of technologies came and went, right? They failed because they weren't the right technologies. I think that's what we'll see now over the next maybe 5 years with AI, is some false starts, some interesting technologies that still fizzle, some sleeper technologies that we look at and go, I don't know. And then 10 years from now, we're like, yeah, this is still a thing I'm using today. And we're all too close to the problem to be able to see how that's going to go. But again, it's happening very, very fast right now. And that's really exciting.
It's certainly been a very interesting shift overall, as you mentioned. So I feel like it's going to continue on being that way for quite a while. It's funny because, to your point as well, I feel that we've really gone from talking about, how can we code in assembly to be able to pretty much make these systems work and understand the ground foundation levels, to now pretty much just having an AI that can write full chunks of code, and
Yeah.
which is basically like being promoted everywhere. So I feel
Yeah.
it's a really big shift of mindset that we're having, and I think it'll be critical as well for developers and people like who are looking to eventually like get into the space too. So I think
Yeah.
it's a very interesting space that we're currently in. But I'd like to shift our conversation a bit now towards the sustainability aspect of this models, because I feel that a lot of people these days have been very glued towards the sustainability element. I personally as well, I feel that sustainability has been taking somewhat of a bit of a backseat as well with all these
So
rapid
true.
developments within
So
Gen
true.
AI. Even the big
Yeah.
organizations like Microsoft or Amazon don't speak of it as much anymore as they used to. I remember in like like pretty much like the reinvents I used to go to like a couple of years ago, where sustainability always took a center stage. It
Yep.
isn't that much anymore, but based on your experiences, I also just wanted to ask, so how are you finding it as well within your developments within WASM 2? Like, have you been finding being able to give you an edge as well, especially for instance when working with different ARM 64s, for instance, with the deployments, or how are you finding it?
Yeah, and I mean, this is such a perfect question because otherwise, I just slid from, we started out with more of a sustainability mindset into, and now we're doing LLM stuff, which is one of the least sustainable, kind of things. But we actually are doing some really fun work in this area, and I always love to talk about it, even though Fermion's not the one who's doing the brunt of the innovation. It's Deep Green and Sivo and places like that. But right when we started this conversation, I was telling you this story about how, this was all about figuring out a way to make better use of the hardware we had, right? We were looking at having virtual machines that were just queued up doing nothing, and that's wasteful. So how do we get rid of waste? Well, we tried to find a faster form of compute that was less wasteful and made better use of its resources. Then you get to LLM inferencing, for example, or generative AI, where we're just consuming vast amounts of GPU power. And these GPUs are drawing huge amounts of power. They have huge numbers of cores. They're just, in one way, they are probably one of the most astonishing pieces of equipment humankind has ever built. And on the other, it's like, yeah, but I kind of feel bad using all that electricity to generate a picture of a dog wearing a party hat for my kid's birthday party, right? How do you solve a problem like that, though? Because again, we really are on track to take a technology that's very, very promising and discover some fascinating new ways to problem solve. But on the other, it's wasteful. So, as we approached building Fermion Cloud, and Fermion Cloud essentially lets you as the developer use our GPU resources to do your inferencing. We wanted to make sure we were doing this in the most responsible way we could figure out how to, right? And that entailed a good, strong sustainability story. So the way Fermion Cloud works is you build your WebAssembly application, you upload it to Fermion Cloud, then you get back your URL and you can execute it. When you're doing your LLM, when you are doing your LLM inferencing, the inferencing is running on one of our GPUs. It's sitting somewhere in a data center. So we said, all right, can we figure out a way to take those GPUs that we're going to host and do something that isn't bad for the world around us, right? And we ended up chatting with a company called Sivo that is a smaller cloud provider when you're comparing them to like Amazon and Google. And they're based in the UK and the West Coast of the United States. We were talking to them about this and they said, well, we're working with this company called Deep Green. And Deep Green is based in the UK. And they're actually heat engineers and not necessarily, hardware engineers, or at least not computer hardware engineers. And they were looking at the problem in a way that was different from our approach. Our approach had been like, how do we consume less electricity, right? How do we generate less waste? And theirs was, how do we take the waste that GPUs generate and turn it into input for a different system? So instead of trying to say, how do you produce less heat off your GPUs? How do you consume less electricity? They were saying, is there a way that we can use that product to do something useful? And their answer was, well, you could heat water. And so Deep Green has been building this system where, I kid you not, you get a rack inside of something that looks like a refrigerator, like on its side, and is submerged in mineral oil. And you basically, so you've got your, say, NVIDIA A100 GPUs. That's what we use in Fermyon Cloud, submerged on a rack in mineral oil. And as you're doing your inferencing on Fermyon Cloud and generating heat, that heat gets transferred through this system into a heat exchanger, which then heats swimming pools or heats large water heaters for condos or apartment buildings or flats in London. And it was such an interesting idea. And so we do this for about 2/3 of our GPUs. But the thing that fascinated me about this was that it took somebody to say, the problem isn't that we're generating too much heat. The problem is that we're using heat as a waste product instead of using heat to do something useful with it. So Deep Green is the company, and I just think what they're doing and their approach is fascinating. And I like that somebody is thinking about using this process in a very new and unique way. They actually say that it is carbon. Okay, I'm going to get the terms wrong. It's carbon negative. It uses less. The carbon footprint is smaller than if we had mitigated all of the carbon that would footprint of the AI GPU and we're merely accepting the carbon footprint of heating the swimming pool. In other words, it's more efficient to do it this way than using, I don't know, whatever gas furnace or whatever the traditional or electric heating would have been. And I think that's very interesting that we might actually be making gains on this, not merely coming out at a zero sum, but coming out doing better than we were before.
That's fantastic to hear. I feel that it's good, a very great thing to have more of these conversations going as well, having more partnerships, having more work doing with these companies that are doing a lot to be able to really move forward the conversation how we can decrease our carbon footprint in using these LLMs, because I feel that with the pace of innovation that we're going, it's sometimes very easy to forget how much of carbon footprint we're actually consuming and putting it in the backseat. So I think it's a really great way of being able to move forward those thoughts again.
And again, I mean, the coolest thing about this isn't that the bottom line isn't, oh, well, you just should use less GPU or you should use less electricity or deal with slower inferences. The outcome of this is, no, you should look at this and say, what's the opportunity? How do we take the byproduct of this thing and turn it into fuel for something else? I just think that that's an attitude more of us need to adapt in many more areas of our life. It was really eye-opening and challenging for me to kind of look at that and say, what other problems could I reframe this way instead of saying, we need a faster horse? It's, we need to figure out a new way to solve or new problems to solve with this technology.
100%. And I feel that's the mindset that a lot of people will have to encompass as well as we continue navigating this challenge.
Yeah.
So moving a bit into looking at the future of these technologies that we're discussing, do you have any particular developments that you would like to share within WebAssembly within the cloud native system? And what do you think the future will look like for how these technologies will really help to move forward the future of both serverless and generative AI?
You're making these segues so smooth for me because I think this actually continues with that idea of sort of shifting a perspective. Here's a problem that I had never thought about before until fairly recently, which was if you look at all the different programming languages and all the different libraries, say we've got JavaScript and we've got Go and we've got C# and we've got Java. We have a YAML parser written in every single one of those languages. We have a network stack written in every single one of those languages. We have a time library for every single one of those languages, and we get zero code reuse across those languages. And I had always just accepted that as the way things were, as the way things had to be. So as we got really involved in the WebAssembly world, one of the things that we noticed was I can run a piece of WebAssembly code in a nice, secure sandbox. And because it was written for the browser, the sandbox was designed so that I could call into that sandbox. And I could basically say, I'm going to expose some capabilities that allow me to call into this sandbox. As we got going, we went, well, wait a minute. If I were to run two things in adjacent sandboxes, I should be able to have one thing call to the other thing, and I, in my intermediary capabilities management role, could say, yeah, component A is allowed to talk to component B. And as we started exploring this concept, we realized that we could effectively start to change the way that this sort of language situation had led us, this environment into which this multi-language setup had led us. And we could say, actually, I can write libraries in one language and use them from another language. In fact, I don't even have to know what language the other thing was written in because it's just a WebAssembly binary. So over the last 3.5 years, actually, it's probably been longer, but 3.5 years has been the really peak activity on this thing. A new specification has been developed inside of the WebAssembly community, and this specification is called the WebAssembly Component Model. Some people abbreviate this to WCM. And the WebAssembly Component Model basically says, here's how you write a WebAssembly module that can communicate to another WebAssembly module, and then here's how the security works between those two. So I can take my date library written in Go and I can call it from Rust, and then I can load that Rust library into, another WebAssembly that's written in JavaScript, and suddenly I have a 3-language binary, and that starts to cut into this requirement that we keep writing the same code in different languages. So ideally, if we did this well, then over time, instead of going to npm to download my JavaScript packages, or Python, PyPy to download, pip to use Python package. You can tell I'm not a Python developer. I don't even know what the package manager is called. Start focusing on one particular language ecosystem. We can have one sort of big registry that has the best YAML parser, the best date parsers, the best whatever, and we don't even have to know what language they're written in. We can just import them into our into our code and use them in a WebAssembly runtime. That's a really exciting possibility for the future here, because we can stop wasting effort writing the same algorithms in lots of different languages. And I think, again, because of that capabilities model, it gives us one further advantage. And, not too long ago, there was a fairly bizarre vulnerability where a very creative hacker went to the XZ project, which is a compression library, and managed to get a couple of commits rolled into that library that would allow the XZ library to attack other websites using code from yet another project. So essentially it was calling out to the SSH library and using a separate thing as an attack vector. Now, how could it do this? Well, it could do this because the way systems work, we compile all of our code into one big binary, and that code can sort of access any other part of the code inside of that binary. And WebAssembly, this whole component model would basically say, no, you can't just access anything from any other part of the library. You can only access what that thing says you're allowed to access, and you can only access it if somebody has granted you the capabilities. So we can turn on and off the ability of XZ to access the network or access the SSH library or whatever, and know that we're protected at a very high level. So I think that'll start to transform the way that we do security and allow us to make much stronger guarantees with security. And that's increasingly an important thing, as almost everything we do now is online, but also as we start to get into generative AI and we want to make sure that that doesn't get used as an attack vector against us. I think this kind of model will really play out over the next several years as a powerful way of rethinking the way that we build applications and the way that we deploy applications. So I think the WebAssembly component model is, up until this point, we've been talking about current technologies and how to do it better, right? How to run faster serverless, how to run more effective serverless. This is the WebAssembly component model, is the thing where we say, okay, this is how to level up serverless, right? This is something new that we could never do before. And now it will be so easy that our developer tools will do it for us, and we won't even have to think about what the upstream language was for my date processor or my YAML parser or whatever. So I think that's going to be really exciting. I still think, the specification just came out, February of 2024, so earlier this year. So I think we're in the early days of this. In fact, it's a great time if you are the kind of person who likes to get in on a ground floor. It's a great time to start playing around with these technologies and build your own tools and start writing blog posts about how to do this kind of thing. But I think it'll take a couple of years before it gets a whole lot of traction. The cool thing about where I'm sitting and how I've been involved in this community is, like, I got to see this thing grow up, and I'm going, this is going to be cool. This is one of those moments where you see a technology and go, this is going to shift the way that people are writing code from now on into the future.
Definitely. And I feel you're very well positioned in innovating and moving it in that direction as well to be able to continue fostering the growth of this technology to be able to further contribute towards the people's growth and how people develop the technology. So it's a really great space. And on that note as well, do you have any tips you would like to share in particular too for those looking to get more into exploring more within WASM as well in terms of both serverless and generative AI?
Yeah. So WebAssembly itself is standardized by the W3C, the same group that standardizes CSS and HTML and all those kind of core web technologies. So there's some great, easy, approachable, primers here and there that you can get to. Bytecode Alliance is sort of the organization that writes a lot of the reference implementations of this. So you can think about, Bytecode Alliance as the ones who are doing the active coding and also sort of writing a lot of the standards. Bytecode Alliance has lots and lots of members, including Microsoft and Fermyon and Google and Amazon and other companies like that. Those places are good places to go if you want to start getting plugged into the community around those. The interesting thing about WebAssembly, both its strongest point and its biggest danger, is the fact that for WebAssembly to work well, every programming language needs to be able to compile to WebAssembly. And that means every programming language community needs to be able to support that. So, for example, C# and the .NET team at Microsoft are working on their version of a compiler from C# to WebAssembly. That's all open source work, and you can go get involved in that. Likewise, Ruby and Python each have their own initiatives to build interpreters that will execute inside of WebAssembly. Both of those are released already, but some other languages are still sort of growing. Right, Java is probably the slowest language in here. I'm not even sure if they've actually started the project yet. Swift, there's been a large community project to do this, and the community project seems to be making its way into the official Apple upstream. So there are all these different language communities. Pick your favorite language, go see what's happening in there. It's a great way to get involved and to start playing with the technology. And then, of course, I'm always passionate about Spin. Spin is Fermyon's easy-to-use developer tool. You can get from blinking cursor to deployed application in 2 minutes or less with Spin. It has kind of the tools built in, works great with Go and Rust and Python and JavaScript and TypeScript and some other languages. So you can always go to developer.fermyon.com and get to all the documentation. You can go to GitHub/Fermyon/Spin and get straight to the source code, or you can go to SpinKube.org, which is the Kubernetes version, and follow the tutorials there and be able to run it inside of your Kubernetes cluster. So those are all great places to get started. I'm a big fan of Bytecode Alliance as a community that's really kind of pushing the envelope right now. There's a WASM conference that'll happen later this year. I think it's going to be co-located with KubeCon in Salt Lake City in the US, but I'm not entirely sure about that. But that's kind of one of those community nexus points. In Europe, the community nexus point is WASM.io, which happens in spring of every year. So it has just happened. It was in Barcelona this year, and it was fantastic. But those are great places to get started.
That's really great to hear. And I'm sure those tips will be very helpful for our listeners who would like to get more involved with WASM. But just wanted to bring this to a close, as that's pretty much all the time we have today. Thank you again so much, Matt, for sharing all your insights with our listeners. And to our listeners, thank you so much again for tuning in. Remember that you can follow along with the podcast at Serverless Sorcery on LinkedIn or on Serverless-Sorcery on X. And for Matt, you can catch him at Technosophos on X and Matt Butcher on LinkedIn. Looking forward to catching you all again in the next one. See you all.